Oh, yeah. I wasn't ready.
Oh, you got
I don't cover anything at all.
Did you watch the game?
It's just like cold when my ears are in.
Yeah, that's what it was.
The poison is starting to take effect.
What?
Okay, guys. Back to our notes. Okay, so we just mentioned the point of inflection is where the guys, where the concavity changes. So concave up, concave down, vice versa. Where it switches, that is our point of inflection. Okay, so let's look at this next example. The graph of the derivative of a function on the interval from -4 to 4, so notice there are no little arrows that keep going. This is it, the whole graph we're looking at right here. Answer the following questions about the original graph of f, justifying each answer with the information obtained from the graph of f prime. Okay, so this is the derivative. This is where we kind of have to look at the graph and think backwards. Okay, on what intervals is f, the original graph, increasing? How would I tell where the original was increasing based on the derivative?
It's where like the y-intercept is positive.
Where the slope of the
You mean where the y coordinates are positive?
Yeah.
Yes. Yes. Okay, so this is the derivative. If my derivative is positive, meaning above the x-axis, then the original function was increasing.
It was like two tests again.
Mm-hmm. Where the derivative is negative, which means below the x-axis, the original function was decreasing. Where it is 0, it is what? What does that tell me?
On the original graph.
It's like where like a peak or a drop.
Okay, could be. It's. We're talking about motion. It's not moving. It's not increasing or decreasing. It could be a max or a min. Yes.
I didn't know really how to explain it, but now that can do it.
Okay, so now let's go back and answer A. Where was the original function f increasing? Okay, and since this says on the interval -4 to 4, I'm going to use a bracket with -4 to -2. Now, can I just say -4 to 1? No, right, you have this 0 value here, which is not positive. It's not negative either. It's neither. So I have to say, okay, this is positive, and then it picks back up just to the right of -2, and it's positive again until 1. So I'll use parentheses there, union -2 to 1.
So if it's a 0, you just use parentheses.
Mm-hmm. Okay, is everybody okay with that answer? Okay, on what intervals was the graph of f concave up?
Maybe the negative. Because they'd be dipping down and going down.
Okay, so well, let's think about this now. Okay, so concavity we talked about before the break is based on the second derivative. Second derivative positive means concave up. Second derivative negative means concave down. This is a first derivative graph. How can I get information on the second derivative?
The slope of this graph.
The slope of this graph. Because looking at a graph, I can tell the derivative information based on the slope. If I have an equation, I will just take the derivative.
That's what I was trying to think of.
So, what is the slope here? Negative. I want concave up, so I want positive slope. Oh, got a little bit of positive slope there from -2 to 0. Well, we'll call it 0, yeah. Do I have positive slope anywhere else?
Yeah.
From
3 to 4.
From 3 to 4. So union 3 to 4. Now I can use a bracket there because I know the graph doesn't go beyond 4. At which x coordinates does f have local extrema? Okay, so mins and maxes, where do those occur?
2, 0, 3.
-2,
-2, 0.
0. No,
I have
-2.
not heard the answer yet.
-2 and 1.
Okay, so
4.
let's look at -2. First derivative is positive, then it's 0, then it's still positive. That means my original graph is increasing, going uphill, 0, and then more increasing.
Is it like a kind of like a stair step?
The shelf point, yes. So my original graph is increasing, little momentary slope of 0, and then keeps increasing. So this is a shelf point. It's not on this graph, but it represents a shelf point on the original. So shelf point on F.
Does that help us with the local?
Okay, so we haven't found a local extreme yet, right? Because I was increasing, kept increasing, hit another slope of 0, and then all of this is where the original graph is decreasing because its derivative is negative. So if I went from increasing, hit a slope of 0, and then decrease, what happened right there?
So did that do the opposite?
Max.
So 0 max.
Okay, so at which x coordinate does F have a local extrema? At x equals 1, there is I'll put max in front there. Is everybody okay with that? Because I went from positive first derivative to negative first derivative. What are the x coordinates of all inflection points? Okay, so an inflection point is where the second derivative changes from positive to negative or vice versa. So second derivative is slope information from this. Negative slope, positive slope. It changed right there. So what also changed? Concavity. So I have an inflection point at x equals -2. Second derivative is negative. Second derivative is positive. That means I was concave down. Now I'm concave up. Okay, well look. Now the derivative changes to negative. So there's also one at 0. Okay, does the slope ever change again? Right here, it changes from negative to positive. So I have 3 points of inflection here. And the reason is the slope of F prime changes from positive to negative or negative to positive. Oh, sketch a possible graph. I'm going to use my pencil in case I mess up. 1, 2, 3, 4. 1, 2, 3, 4. Notice on these questions, we're only asked at what x coordinate. Why didn't it say, like, what is the point of inflection? Like the ordered pair.
There's no y coordinate.
Yeah, I don't have an equation. All I have is this graph. So I can't possibly find the y's that go with these without the original equation. I can just tell you where they happen. I can't give you the ordered pair on the original graph. Okay, so from the beginning, we are increasing. And I know that because I have a positive first derivative. Okay, where do we start? I don't know. That's kind of up to us. But then I do hit the slope of 0, and then I keep increasing until I get to 1.
So would it be like a?
Remember we said we have a shelf point. So since I'm increasing, I'm going to start down here a little ways. Okay, so at -2, I have a shelf point. All right, so I'm going to increase to -2, hit that little slope of 0, and then I'm going to increase some more. Now, do I increase like this or like that?
Second one.
How do we know? You're right.
At some point, so it's gonna hit 0, right? So when you do it like that, wouldn't it be a discontinuity?
Okay, look what we said over here. Where do we have a point of inflection? -2 was one of them. And a point of inflection is where concavity changes. So right here I have concave down, and I know that because this slope is negative. So I'm increasing because the first derivative is positive, but I'm concave down because the slope of the first derivative graph is negative. That's a whole lot to take in. Okay, let me say that again. Okay, so over here, let's do this. From -4 to -2. Okay, f prime is positive. F double prime is negative. Okay, so how did I know that? This is the first derivative graph. I know it's positive because these values are above. I know the second derivative is negative because now I'm just looking at the slope of this graph, and the slope is negative. Okay, so if your first derivative is positive, it means your graph is increasing. If your second derivative is negative, it means you're concave down. So how do I increase and concave down? It's like this. Okay, but from -2 to 0, both derivatives are positive. First derivative is positive because it's above. Second derivative is positive because I have a positive slope. So if both are positive, that means it's increasing and concave up. What would that look like? This. Increase, concave up. So I know I have to turn it into something like this. Okay, until what point? Remember at 0 we had another point of inflection. We are concave up until we get to 0. And then we're concave down because we're not concave up again until 3. Okay, so I'm going to go like maybe not so steep. Okay, but then I have another point of inflection. So that means it's going to change concavity. So right there I have concave up, but right there I need concave down. Okay, so at 0 the concavity changed because this slope changed. Now at 1 I have a first derivative of 0, then it becomes decreasing. So at 1 I'm going to hit that max and decrease some more. Keep decreasing until I get to 4. But remember at 3 there was another point of inflection. So I'm going to keep decreasing until I get to 3. And then I have to change concavity. So somewhere right in here, can you see that the concavity changed from down to up? These are not easy. It's a lot of information. Okay, now is that exactly what the graph looks like? We don't have exact points, so we're not sure, but it's that general shape. What do you have a question about?
It's down which was like back more. Not really the graph, it's C.
Okay, in which x-coordinate does the function have a local extrema? Okay, so all we're looking at on this is where does the first derivative go from positive to negative or from negative to positive? Okay, positive stayed positive. But right here it goes from positive to negative. So that is my only extrema point. And if it went from positive increasing to negative decreasing, it had to be a max.
Oh, because it's the first derivative.
It's first derivative.
You
You got it. Yes. It's a whole lot of information there. All right. Since we're talking about that, let me give you this little kind of a cheat sheet. This has a whole bunch of just summary that I would read through, but this little table is useful. So take a look at this. It bases what the graph looks like by the first derivative sign and the second derivative sign. So if I know my first derivative is positive, that means the graph is increasing. And if the second derivative is positive, that means it's concave up, which means the graph looks like that. So it helps us sketch graphs based on the signs of those values. First derivative, second derivative.
So first derivative tells you if it's falling or rising, and then
Correct.
second derivative tells you
Concavity. Exactly. And so these are the 4 combinations of things that can happen. So we talked about both being positive. What if the first derivative is positive? That means you're increasing. But second derivative is negative. That means you're concave down. The only way you can increase and be concave down is if the graph looks like that. Okay, what if first derivative is negative? That means decreasing. But second derivative is positive. That means concave up. You can be decreasing and concave up if that is what your graph looks like. And then if both are negative, it means you are decreasing and concave down, and that is what the graph would look like. So nice little cheat sheet there to help us when we are sketching things. Okay, next example. Be careful not to assume that a point of inflection occurs at any value where the second derivative is 0. Just like, flip back here. Just because I had a first derivative of 0 didn't mean that was a maximum end, right? Because it went from positive and stayed positive. So the same thing goes for second derivatives. The second derivative can be 0 at a non-inflection point. For example, the function x to the 4, what does that graph look like?
Is it like a W?
If I had more terms added, it would be. If it's just plain old x to the 4, it's like a narrow parabola. Okay, with no other terms added there. Second derivative is 12x squared. Okay, so I'll skip the first one. First one is 4x cubed. Second one is 12x squared. If I set 12x squared equal to 0, I get x equals 0, but that is not an inflection point. Okay, so if that was the graph of x to the 4, there's no inflection point. Concavity doesn't change there. It's concave up for the whole graph. So we just have to be careful. So guess what we do to define those? Do you remember what those things were called that we did before the break? These things? Sign charts. So we do sign charts for second derivative to see where the concavity actually changes. Okay, so therefore the only safe way to test algebraically for a point of inflection is to confirm a sign change of the second derivative. This could occur at a point where the second derivative is 0 or undefined. Fails to exist. Okay, so here we go. A particle is moving along the x-axis with this position function for x greater than or equal to 0. Find the velocity and acceleration and describe the motion of the particle.
first derivative, second derivative.
Yep. Okay, so velocity is first derivative. Acceleration is second derivative. Okay, so we're going to investigate here and see what's going on without even looking at a graph. Okay, what is our first derivative? 6x squared minus 28x plus 22. Ooh, I want to know where this is 0 or undefined. Is that ever undefined? No. Is it ever 0? Probably at a real number. Could be imaginary, but how do we find out? And then do what? Okay, how many of you, let's see, I don't think I want to try to factor that just yet, but what if I divided everything by 2? Would it make it a little bit easier? And I would still be dividing the left by 2. It would still be a 0. So 3x squared minus 14x plus 11. That's a little bit easier to factor. Does it factor?
Yes.
It does. Okay. All right, so let's look at the first term. What factors would give me 3x squared? 3x and x. Go to your back number. 11. There's only two factors I can use, 11 and 1. Does it matter where I put them?
Wait, yeah.
Absolutely, because this number here is going to get multiplied by 3 when I FOIL it out. So I need 11 here, 1 here. This is 11x in that inner product, 3x in the outer product. How can I get negative 14? Both negative. You got it. All right, so if I set this factor equal to 0, what is x? 11 over 3, and this one, 1. Okay, I'm going to set up a sign chart. Which is smaller, 1 or 11/3? 1. Okay, so let's test a point to the left of 1. What's super easy? 0. Okay, it's easy to put it back in this one here or this one up here because subbing in 0 will give me what kind of number, positive or negative? Positive, which tells me this is increasing. Okay, now if I'm talking about a particle here, what does this mean? Moving in a positive direction. Positive velocity would mean positive direction. So forward or right or up. Okay, positive direction. Okay, what's something easy here between 1 and 11/3?
1.5.
Oh, even
Wait,
easier.
2.
How about 2? Yeah.
Oh, shoot.
That's okay. All right, so let's go back to our original here.
This like makes more sense now after doing this too. 'Cause
Good.
I didn't even understand if you had two numbers, you had to do a number in the middle. That was like confusing.
Yes, so you're always split it into regions and you're picking a number from each region. Okay, so 6 times 2 squared. 24. I'm going to come down here and write this. So I'm subbing in 2. Okay, so I got 24 minus 28 times 2 is minus 56. So far I'm negative. Plus 22. Okay, so that's 46 minus 56. What kind of number is that? Negative. Use a calculator if you have to. Okay, what's a nice number to the right of 11/3? Yeah, that's 3 2/3, right?
Yeah.
So let's try 4. So I'm going to sub in 4. Okay, oh, we might need a calculator here. I don't know if my brain is back working well enough to do that one in my head. Let's see, 6 times 16 minus 28 times 4 plus 22, yes, it is positive, which tells me increasing. Okay, so in terms of the particle's motion, I am moving in a positive direction, then a negative direction, then a positive direction again. Okay, so now let's look at our second derivative and then we'll piece it all together. Second derivative is almost always easier. Go back to the original derivative, not where we divided everything by 2. 12x minus 28. Okay, that is never undefined, but it is going to equal 0. Okay, so if 28 equals 12x, what does x equal? So 28 over 12, 14 over 6, 7 over 3. Got there eventually? Okay, we have to do a sign chart. Marking 7/3. Okay, in terms of motion, what is the second derivative giving us? Acceleration, right? Acceleration. Velocity was the first, acceleration was the second. Okay, so something to the left here, 0, 1, okay, either one of those. Positive or negative? Negative. Okay, now if I were graphing a function, I would say it's concave down, but this is negative acceleration. I'm just going to write negative acceleration. But if I were just graphing a function, it would mean concave down. Okay, something easy to the right of 7/3. 3. Okay. 12 times 3 minus 28, positive. So I have positive acceleration. Okay, so to describe the motion, I would say we are moving in a positive direction. Where? Or when, I should say. Okay, and remember it said greater than or equal to 0. So we're going to start at 0 until 1. 0 to 1. And then again, so union, 11/3. I suppose it's just infinity. Because it didn't cap off the time or the x value there. Okay, moving in a negative direction. Okay, from 1 to 11/3. And that's it. Okay, positive acceleration. 7/3 to infinity. Negative acceleration. Remember, it just starts at 0, so from 0 to 7/3. Okay, now here's my question for you. When is this thing speeding up and slowing down? Do you remember how we determined that? It's been a little while. Okay, speed is the absolute value, but I'm not asking you to find the speed. Like, when is this object gaining speed and losing speed? Okay.
Anything greater than 7/3 no.
Okay, here's the key. If acceleration and velocity have the same sign, you are doing what? Speeding up. If acceleration and velocity have different signs, then they are working against each other.
So then it'd just be 11,
And you are slowing down. Okay, wait. Okay, say that again.
It'd be anything greater than 11/3.
Is doing what?
It's speeding up.
Okay, I agree that we are speeding up from 11/3 to infinity. Because, remember, look, 7/3 is somewhere in here, right?
It's still negative.
Okay. But to the right of 11/3, both of these are positive. Definitely speeding up from 11/3 to infinity. Because both are positive. Are they both positive anywhere else? Okay, are they both negative anywhere?
From 1 to 7.
From 1 to 7/3. So we are also speeding up from 1 to 7/3. Both positive, both are negative here. Okay, so if we know where we're speeding up, anywhere else we must be slowing down. Velocity and acceleration are opposing each other. So we're slowing down. At the beginning, at 0, we had positive first derivative, but negative second derivative. So starting at 0 to when? 1. Okay, because remember, between 1 and 7/3, they're both negative. So that was speeding up. Okay, so what happens at 7/3 then?
Wouldn't it be like a point being up? Not
Between 7/3 and 11/3, first derivative is negative, but this one is positive. So that means we are slowing down from 7/3 to 11/3.
weird, but it's like, where's the point of inflection?
Okay, so if we were just graphing a function, our only point of inflection would be at 7/3 because that's where the second derivative changes, and it went from concave down to concave up. Okay? Yes, guys.
This was, I think this is a little bit of a but it's like towards the top.
Mm-hmm.
What was it? It's like the number 2 thing. It's like the function, like 2 root of x. It has a second derivative of like, then it's like negative for 9x.
Yeah,
I
funky.
got like 3 of those on the homework, and I just put x equals
Okay,
like
well,
0.
all right, we'll look at those soon. Oh, and I always forget this every time. Here was our summary back here. So let's go ahead and fill in what we didn't talk about. Okay, so we already talked about moving to the left, moving to the right. But what if we were just graphing f? Do we have a min and a max anywhere? How do I determine that? If I'm just graphing this function, would it have a min, max, both, neither?
Yes, but
How do we know?
it continues until it has one at all.
First derivative changes from increasing to decreasing, and then decreasing to increasing. Okay, so what happens at 1? Min or max? Max, yeah, just follow the arrows. You top out there. And then there's a min at 11/3. Okay, so let's flip back and answer that question. So we already answered the first 2. We do have a minimum at x equals 11/3. It has a maximum at x equals 1. I could find the ordered pair if I wanted to because I have the original function to plug this in. Okay, concave up, concave down is concave
Up
and concave down.
from 0 to 7.
Okay, good. All right, so let's fill that in. We are concave up from 7/3 to infinity. Concave down from 0 to 7/3. Acceleration positive, negative, we already answered that. Point of inflection at x equals 7/3 because the second derivative changed from negative to positive, from concave down to concave up. So 7/3. And again, I could find the ordered pair if I needed them by plugging these numbers back into the original function. Okie dokie. Okay, example 5. Did I skip example 4? No, I didn't. Okay, example 5. Use the second derivative test to find the local extreme values of this function. Okay, so what this says, look right above here, it says, if your second derivative is negative, then you have a local maximum at this. And if the first derivative is 0. First derivative is 0, second derivative is positive, you have a local minimum. How else can we find that out, though, where the minimums and maximums are? Just from the first derivative sign chart. So that's actually what I'm going to do. I'm not going to use my second derivative. I'm just going to make a sign chart of the first.
We're going to be forced to use that? Or can we just
No,
do that?
yeah, use whichever tool you have to figure that out. To me, that seems like overkill, so I'm going to do the sign chart. Okay, first derivative is 3x squared minus 12. That is never undefined, but it will equal 0. Okay, move the 12 over and I have 12 equals 3x squared. Why did I move the 12 over and not leave it equal to 0?
I have no idea what you're doing. Unless you're going to divide by 3.
Like over here, we factored. Why didn't I try to factor that? There's just one term with an x. So I'm just isolating that term with the x. Okay, so a whole different type of quadratic equation. Yes.
I was like, whenever I got to this point, and I'll like notice that, but I just couldn't do quadratic formula.
You can, absolutely. Quadratic formula will work with any quadratic equation. Sometimes I heard it referred to as using a bazooka instead of a fly swatter. It's like kind of overkill, more work than necessary, but it will work every single time.
The quadratic formula at one time in class, I just like remembered it.
Then go for it, because it will work every time. It will work every time. I like factoring, so I tend to always look for factoring first. So, you know, but yes, quadratic formula will always work. Okay, if I square root this, what am I at?
2.
Plus or minus 2. Okay, sign chart. Negative 2 is smaller, positive 2 is larger, so put them in the appropriate place. That gives me 1, 2, 3 regions to test. Okay, let's take negative 3 and plug it into this derivative. Do I get a positive or a negative? Positive number. That tells me my graph is increasing. Okay, 0 is pretty easy. 0 gives me negative. Tells me the graph was decreasing. And then let's use 3. Sub in 3. Another positive. Increasing. Okay, so now the local extrema are pretty easy to find. Okay, what do I have at negative 2? And here? Yeah, follow the arrows. So I have a local max, and I'm saying local because that's what was in the directions, but then we'll talk about how we would know it's not absolute in just a second. At x equals negative 2. Okay, let me come back to that. Local min at x equals 2. Did I answer the question? I don't have, it did tell me to, but I already know this with the first derivative sign chart. So I don't have to do that, but I still haven't answered the question. Why? Find the local extreme values. What is that asking for? The y's. Not where, but what is the extreme values? Okay, so it's true. It occurs at x equals negative 2, but I need to sub negative 2 into this to get what that max is, and then positive 2 needs to be subbed in to figure out what the min is. Okay, so max of, max of, all right, let's sub negative 2 in. So negative 8 plus 24 minus 5. 11. At x equals negative 2. A min of, now I'm going to sub 2 in, so that's 8 minus 24 minus 5. Negative 21 at x equals 2. Okay, now I've answered the question in full.
All the math, like all this stuff isn't like easy concepts. It's just there's so much.
I know. It's so much algebra. Okay, how, if this didn't say local extreme, how would I know there were not absolute max and mins on this graph? What? What keeps going? How do you know? X cubed. What's X cubed graph look like?
It's got a shelf in the middle.
Possibly. Now it could be like this. But either way, that in behavior, one end is going up, one end is going down forever. There's not an absolute maximum end. Just because I know what X cubed looks like.
So if it ever asks us for a local extreme like value at a time, that just implies that the graph line doesn't stop.
Yeah, or it's just saying in this area, even if it does stop,
It
find
gives
the
you, like,
local.
intervals,
Right. Exactly. Yep. Okay. Whew, it's a long lesson, isn't it? All right, 2 more. If this is the derivative, identify where the extrema occur, find the intervals on which f is increasing and decreasing, find where the graph is concave up, concave down, then sketch a possible graph. Just a few things to do. Yeah, exactly. Okay, I'm going to work up here because that looks like it might be limited space here. Okay. That is already the first derivative. So if I want to know where the extrema occur, I don't need to take the derivative. That is the first derivative. All I want to know is where is this equal to 0? Okay, what were you about to suggest?
Oh, I was just trying to factor out already. Sorry. Where you could like factor in 4x squared.
Absolutely. That's exactly what I would do next. Times x minus 3. Huh, look how easy that is. Set this factor equal to 0. Set this factor equal to 0. If I divide by 4 and square root, what is x? And what is x here? 0 and 3. Okay. Not too bad. All right, let's make our sign chart for the first derivative. 0 and 3. Okay, so let's choose -1. If I choose -1, I'm gonna think about these factors. If I sub -1 into there, that's still going to be a positive. And -1 minus 3 is a negative. And a positive times a negative is a negative, which tells me the graph is decreasing. Okay, let's sub in 1. 1 gives me a positive there. 1 gives me a negative there. Positive times a negative. Ooh, I still have a negative. It's still decreasing. What happens at 0? Shelf point. I was decreasing, had a slope of 0, kept decreasing. Shelf point. Okay, let's try 4. Subbing 4 in, that's positive, positive, positive times positive is positive. It is now increasing. Okay, so we could go ahead and answer A and B. Okay, let's do the increasing, decreasing. Increasing from 3 to infinity. Decreasing from negative infinity to 0, union 0 to 3. I can't include 0. I have to skip over it because it's a slope of 0 there. It's not a negative slope. Okay, so now I'm kind of working backwards. I did B first. Now I'm going to answer A. Where are the extrema? Min at 3. And I know it's a... Actually, I don't... It would have to be an absolute. What would the original function be? Not the whole thing, but just the first term.
It'd be 2x4.
Something next to the 4, right?
Yeah.
X to the 4, actually. Just plain old X to the 4. So that's like a W or a parabola. So it would actually be an absolute. Min, that's okay.
Wait, so it's the backwards derivative of what I just said about, right?
Say that again. What?
I don't know, it was like 4x to the third, wasn't it?
If you did the antiderivative of that, it would just be x to the 4.
I thought it was divided by 2 the very first time. Divided by 2.
Add 1 to the exponent, which is 4, and divide by 4.
Divided by 4.
Mm-hmm. Okay, so can I plug in 3 to the original function? No, because remember there could have been a constant at the end where the derivative was 0. So I'm going to change that to just x equals 0. Because I don't have the full original function. Well, that's just messy. Let's do that better. At x equals 3. Okay, I don't have a max, do I? Okay. Alright, so that's a and b covered there. Now, for concavity, we need to do the second derivative. Okay, so here is the first derivative. So second derivative is 12x squared minus 24x. Okay, that's never undefined, but it will be 0. Okay, how would you treat this one? You could do quadratic formula if you wanted. Factor out 12x. Okay, what I would do, x minus 2. So if I set 12x equal to 0, what is x? If I set x minus 2 equal to 0, x is, so I get 0 and 2. Okay, sign chart. So this is my second derivative. 0, 2. Okay, so when I pick these points to test, I'm plugging them into the second derivative. So let's take negative 1. Plug it in, tell me, do you get a positive or a negative? Positive. Tells me what about the graph? Concave up. Okay, definitely I would use 1 here. Sub 1 in, tell me what you get, positive or negative. Okay, which indicates concave down. And then let's sub in 3. No. Positive?
Yes, positive.
You checking it? All right. Fact check us.
Yeah, it's positive.
He's testing. Drum roll. Okay.
Yeah.
All right. So find where it's concave up, concave down. Okay. Concave up. Negative infinity to 0. Union 2 to infinity. Concave down 0 to 2. And last question, sketch a possible graph. Woo! Let's see, let's squeeze this in over here. Okay, what are some important points on my x-axis?
0, 3,
And 2, okay. Okay, so, alright, let's look at this, guys. To the left of 0. I think that's enough. To the left of 0, first derivative is negative, second derivative is positive. Decreasing concave up. Use your cheat sheet if you can't visualize it. If I'm decreasing in concave up, what does my graph look like? That. Okay? So I am coming into, we'll just say the origin, like that. Okay? But between 0 and 3,
They match.
I'm decreasing again. And I'm concave down until I get to 2. I have points of inflection at 0 and 2, don't I? Okay, this was concave down, so guess what I'm going to be now? I mean, that was concave up, my bad. Now I'm going to be concave down until I get to 2, and then it's going to become concave up. I had that minimum at 3, so I'm going to come down here and hit a minimum, something like that. Point of inflection at 0, point of inflection at 2. Ooh, last one. Just jumping back in, aren't we? Brains are going. Firing on all cylinders. Ooh, last one. These are, to me, easier to graph when they give us a table of information like this. Okay, so what I don't see in example 7 is an equation anywhere. I don't see an original, I don't see a derivative equation, I don't see a second derivative, but I think it's easier.
I guess we can do it equal.
We can.
We gotta go home, you said? Okay.
A function is continuous. What does that mean?
Means it doesn't break.
No break. On its domain, -2 to 4. Oh, means I have a small little graph to worry about from -2 to 4. Okay. All right. Oh, look, this is nice. F of -2 is 5. What does that mean?
Where -2x
Yeah, there's an ordered pair on this graph. So on this one, I have the exact information. There's a point -2, 5. That point is on this graph. Okay. F of 4 is 1. What does that mean? There's a 0.41 on this graph.
So those are your maximum points, right?
Could be. Possibly. And the first and second derivatives have these properties. Okay, so let's read this. Between -2 and 0, both derivatives are positive. Okay, first derivative positive means increasing. Second derivative positive means increase. Come on, we can do this. It means concave up. If you are increasing and concave up, what does it look like?
It's a curve coming like this.
Increasing concave up, it looks like that.
It's the right side of the parabola.
Okay, right side of a normal parabola. That's a good way of thinking about it. Between -2 and 0. Oh, it means we're going up, aren't we, from there? Okay. When I get to 0, neither of these exist. What does that tell me if the first derivative doesn't exist? But it was continuous. Can't have an asymptote because it's continuous. Corner or cusp? Yeah. So this is curved coming in, so that's going to be a cusp. Right, corners are when you have like lines coming in. This is curved. Okay, so I have a cusp. Oh, okay. Between 0 and 2. First derivative is negative. It's coming down. But second derivative is positive. Concave up.
It's the left side of the parabola.
Okay. Decreasing, concave up, looks like that. So that's what we're doing here. Between 0 and 2.
They match up with it.
0 and 2. Okay. Something like that. When I get to 2, both are 0. So a leveling out, right? Between 2 and 4, both of these are negative. That means decreasing and concave down.
The right side of the upside down graph.
Decrease, concave down.
Let's go.
Like that.
That is how I remember it.
Okay, so let's see. Something like that. Okay. All right, now I'm going to answer the questions. Find where all absolute extrema occur. Okay, and notice it says where they occur. Okay, so I have an absolute max at x equals 0. Do I have an absolute min? Yeah, x equals 4. And I know that's an absolute min because remember the domain just went from -2 to 4. Okay, so number 2, find where all the points of inflection occur. I wouldn't so much as look at my graph, I would look at the second derivative. It was positive, stayed positive, changed to negative. So that means right here at x equals 2, I had a point of inflection. So point of inflection at x equals 2. And then 3, we already sketched it. Ooh. Considering y'all had a week in between, I think you did pretty well. I think you did well.